In this video, we're going to be continuing on with our Truths Behind the Titanic mini-series. And now we're going to tackle some of the real meat of the data science, in this case, regressions. We'll be looking at a few different kinds of regressions, but before that, we're going to look at what's the point of a regression. The point of a regression is to build some kind of model to predict something. In this case, we're trying to predict whether a passenger will survive or not survive the Titanic based on some attributes about that passenger. Namely, those attributes are the columns of the data set we saw in the first video. But in the end, we want to have a high accuracy as possible. So whatever model we build, we're going to take some testing set, which this model has never seen before, and we're going to put that testing set into the model and see what accuracy, what percent it predicts correctly for survival rate. So towards that end, before we get into our different kinds of regression, we're going to look at what's the accuracy to beat. And we're going to define this as basically a very dumb method. Basically, if we have no model whatsoever, we're just going probabilistically. What's the baseline that we need to beat? So that'll make more sense as we talk about it. So this is all based on that one number. So what was the percentage of people that survived the Titanic from our data set? So if you go back to that video, or I can just tell you, it was 38.4%. So we had a 38.4% survival rate. Now, based on this, if you don't want to do regression, if you don't want to build any further models, what's the best probability of success you can do? So that means if you just have person after person come to you and they say, hey, did I survive the Titanic? You either say, yes, you did, or no, you did not, just based on this probability. So basically, here's what that means. So what's the probability that you'll basically guess somebody, their survival rate correctly? So probability of success, which means what's the probability that you'll guess their status correctly. So you succeed if they survive and you guess survive. So basically we can break this probability up into two different mutually exclusive probabilities. So probability of success is probability that they survive and you guess survive, plus probability that they don't survive and you guess no survival. So now what's the probability of the first one? What's the probability that they survive and you guess that they survive? These are actually independent because your guess in this case has nothing to do with whether they survived or not. You have no idea. You're just basing it on this probability right here. So what's the probability that they survived? So it's going to be 0.384 as we saw from the data set. And what's the probability that you guess that they survive? So again, that's 0.384. So I guess to help you kind of understand what's going on here, this is as if you're taking a spinner and you're just spinning it. And 38.4% of that spinner says survive, and the other 61.6% says not survive. And wherever that spinner lands, that's what you guess for every person that comes to you. So the probability that you guess that they survive is this 0.384, and the probability that person actually did survive is again 0.384. Now, the other part of it, what's the probability that they don't survive, is basically the opposite of this, which is 0.616. And what's the probability that you guessed that they didn't survive, which is the probability that your spinner lands in the other region, the don't survive region, which is 0.616. So if we add this is 0.384 squared plus 0.616 squared, we get 0.527. Which means that your probability of success of guessing any person that comes to you correctly is 52.7%. This is the probability to beat, and this is why. If we build some model and let's say its accuracy is 50%, then that model is pretty much useless, because if we didn't use that model and we just use this very, very basic, simple strategy of just spinning our spinner to guess whether someone survived or not, we would still get a 52.7% accuracy on average. So that 50% model is complete garbage. So keep in mind that every time we do a regression here, we need to beat this 52.7%, or else that regression is completely wasted. So now let's get into the regressions, which is the point of this video. The first one is logistic regression, and this is the kind of regression that should scream to you in this kind of problem. So if you want to check out my video on logistic regression to get a refresher, please go ahead and click here and watch at least a few minutes of that video to get the gist of it. We'll review a few of the topics in a second here. But the point is this. So we're trying to predict what? We're trying to predict survival, right? So we're going to label this graph's y-axis exactly as that, so survival. And the x-axis, we're going to go ahead and say it's fair, how much you paid to be on the Titanic. So this is a very simple model. We're trying to predict survival based on how much you paid. And as we saw in the previous video, the correlation also goes with this idea, but the more you pay, the better your chances of survival were. That kind of makes sense because your fare is kind of correlated to which class you're in, first, second, third class. So if you're in first class, maybe you had better access to safety, things like that. So anyway, how would this graph look? We'll look at this exact graph in a little bit in a little while, but for example, we just need to kind of get a gist of it. So this fare is a continuous variable, right? So it goes from 0, and if we look at the data, the highest one is a little less than 550, I believe. So the fare goes from 0 to, let's say, 550, and it's continuous. It can really take any value between these. But what is not continuous is survival. This is either 0 or 1, right? Because so the spectrum is kind of not needed because it can never be 1/2. You can have a person who survived 1/2. Either they did not survive or they did survive. So let's say, just for sake of example here, we have some fares down here. So some people who paid a little bit of money, unfortunately they did not survive, so we plot their points. So we plot some of their points down here. Some of the people who paid a lot of money, maybe in this region, maybe they did survive. But of course, the life is not as simple as this, and the model, the actual data we have is not as simple as this either, because we have people in all regions. There are people who paid a lot over here and still did not survive. There are people who did not pay as much and still they did survive. And there's different combinations like this. But the one gist to take away from this is that we can't have any points which are greater than 0 and less than 1, because no one can have a survival which is not 0 or 1. And we are expecting that there are more points, more survivors towards the higher end of the spectrum of fare, and less survivors towards the lower end of the spectrum of fare. Maybe that's true, maybe it's not. We'll look at the exact model, the exact picture, as I said, in a little bit. But let's just say the picture looks something like this. A logistic regression, the shape of it is an S-curve. And the S-curve is trying to kind of get as close to these points as possible. It's asymptotes trying to get as close as possible. So what that means is kind of like, the shape might be kind of like this. The logistic regression, and how the logistic regression classifies. So this is we'll look at the exact formula of it in just a second, but given our formula, given this logistic curve right here, how it classifies whether it thinks someone will survive or not survive is it bases it on this 1/2. So for example, if you were to put in this fare right here, you trace up to where it hits the logistic curve, it hits above 1/2. So this is basically saying that for this fare, we predict the probability of success is something like 0.7, which is greater than 0.5. Therefore, we think that person will survive. Now, if you choose a fare value that's down here, and then you trace it to the logistic curve, then this is below 1/2, right? So maybe something like 0.25, maybe a fourth. So since their probability of survival is less than 1/2, we go ahead and classify them as not survived. And that's how the logistic model works. Now, of course, it can misclassify because, for example, it's going to misclassify this person because this person's fare was this much, so we trace it up to the logistic curve, and we get a very high value over here. So we're going to say that person survived, but of course they did not. And of course, it'll misclassify. Let's put a more obvious misclassification. Let's say there was a person there. It's going to misclassify them because if you trace them down, it's going to hit the curve right here, which is very low, and it's going to say they didn't survive, but they did. So of course there's going to be misclassifications, but the real question is, does the accuracy measure up to something higher than 52.7%? So actually I think we're going to do the formula right here. But basically the logistic formula, just a refresher, if you need to know the exact details of it, go ahead and watch the video that was linked previously to the logistic regression. But the logistic formula is probability of survival in this case is going to be 1/1 plus e to the negative beta naught plus beta 1 f. In this case, f stands for fare. So basically that means beta naught and beta 1 are the regression coefficients, which kind of determine the shape of this curve. But if we have beta naught and beta 1, we go ahead and throw in the f, which is the fare, and then this calculates the probability of survival. So remember, if it's less than 1/2, we say they didn't survive. If it's greater than 1/2, we say they did survive. And that's how logistic regression works. Now, before we look at the results of the logistic regression for throwing in different variables, let me mention that this was basically just fare on survival, right? So, but logistic regression can be done in a multivariable case. So we can throw in not just fare, we can also throw in variables like sex. We can throw in variables like passenger class, like age, number of parents, children, things like that. This is just to kind of show you what's going on. So this is one kind of regression. Let's compare this against a different kind of regression that's not necessarily made for classification, which is just our simple linear regression. So we're going to look at some kind of adapted linear model. So first you're thinking, how can we use a linear model for this? Because a linear model will probably do very terribly, right? So if we were to just kind of draw what a linear model would look like in this case, maybe, and I'm just kind of eyeballing, it's going to look like this red line right here. And you're saying we're going to get a 0% prediction rate, accuracy rate for this, and you would be correct. Because no matter what you predict, let's say you choose this value of fair over here, you trace it up to the linear model. The linear model predicts something that's between 0 and 1, which can never be the correct value because the correct value of survival is either 0 or 1. So very, very few cases, probably 0, we're going to get the actual 0 or 1 that we're seeking. So we're going to get 0% survival rate. But that's why we're calling this the adapted linear model. So the adapted linear model is basically taking the logic of the logistic model and applying it to the linear model. So what that's saying is, let's do some math here. The linear model looks like what? So we're predicting survival based on beta naught plus beta 1 times fair, right? So based on some fair, we're predicting whether the person will survive or not. And as the linear model is now, as we saw on the previous page, it's going to, most of the time, S is going to be between 0 and 1. Sometimes it's going to be even less than, if we have fairs down here, it's going to be negative. And if we have fairs up here, it's going to be like greater than 1, which is impossible. But anyway, so it's trying to predict the survival based on beta naught plus beta 1 times fair. Now, what if we just kind of apply the same logic as the logistic model? We say that we don't just take S as is because it's never going to be correct. Instead, what we do is we say if S is less than a half, then we set S equal to 0. If S is greater than or equal to a half, we set S equal to 1. So that means the linear model is always going to give values which are 0 or 1, not any continuous range. We're basically just making a piecewise function here. We're saying that, so this 1/2 line, where does it hit the 1/2? It hits it, let me choose a different color. This is getting kind of messy, but it hits the 1/2 line right here. So we're going and say, okay, so all these values right here, we're going to just map down to 0, and then all the values up here, we're going to map up to 1. So at least it'll have some positive accuracy rather than 0. So now the real question is whether the adapted linear model, which predicts either 0 or 1, or the logistic model, which also predicts 0 or 1, is the better model. And for that, we're going to just go ahead and show you the results. So these are our results. So let me explain this table really fast. All these numbers you see are in percentages. And this column right here tells you which variables were used for the regressions. So in this case, this was just fair. This was just sex. This was just passenger class. This was fair and sex. This is fair and class. This is class and sex. And this is all three together. So these last 4 cases are multivariate regressions, and these first 3 are just univariate regressions. And the other 2 columns are the logistic accuracy, which means what percentage of the testing set was accurately predicted with the logistic model, and the percent of the testing set accurately predicted with the linear model. So let's notice a few things. First, let's notice that if we look at every value in the linear model, it is either higher or equal to the value in the logistic model. Here we see it's a little bit higher, here it's equal, here it's equal, here it's a little bit higher, here it's a little bit higher, here it's equal, here's a little bit higher. Now it's not really anything drastic. Here it's usually like a 0.1%. It could just be an error. And I should mention how I got this. So I got these by doing 1,000 runs. Basically you take the data set we have and you partition it, and I took 90% of it as the training set, which went into the model to help build the model, and the other 10% was the testing set, which is how we got these accuracy probabilities right here. But we did 1,000 runs of that. Each of those 1,000 runs, we took a different random 90% sample to kind of diversify it, and then we did an average of the accuracies of the testing set in each case. So this is well diversified, but still we can get some noise here and there. So that this little deviations might just be a result of the noise. But we see that we have either greater than or equal to accuracy in the linear case, which is interesting and is a little bit strange. But we'll see why that is when we see the exact graph of all of these things. But let's notice a few other things. Remember the probability of the beat is 52.7%. Every single one of these beats that. So we have successfully beaten the crude probability, and our models are taking into account some of the information which is relevant, and we no longer need to just use that crude model. In some cases, we have quite a drastic jump. In this case, 79% versus the crude probability of 52.7. That's quite an improvement. So there's that. But let's also see something. Let's look at the univariate cases: fair, sex, and class. So fair and class kind of do the same at predicting accuracy. But interestingly, sex has such a higher accuracy. It's over 10% higher than both fair and class. So that's kind of interesting. This kind of says that sex is out of these three at least, sex is the highest accuracy predictor of survival, which I wouldn't have guessed right away. I would have thought it was something more like passenger class or fair, or a combination of the two. Now let's look what happens when we combine and make multivariate regressions. So let's look at, for example, fair and sex. Fair and sex is 78.2% in the logistic case. Now, how does that compare to taking either one alone? It's better than taking fair alone, and it's worse than taking sex alone. So it's actually reducing the accuracy in this case, and it's doing the same thing in this case. So we probably don't want to use this because it's not even as good as doing a univariate regression. Fair and class. Fair and class is 67.8%, which is better than just fair, and it's kind of the same as just class. And in this case, again, we have the same story. So we see those kind of things. Now, the main thing we're interested in is, what if we take all three together? Is that just kind of destroying our accuracy, or is it building upon it? So if we take all three together, we get 78.7% in the logistic case, which is the same as we got taking just sex alone. So why would we take three variables when we can just do one and get the same accuracy? In this case, we have 79% if we take all three in the linear case, versus the 78.7 that we see in the case of just sex. So, I mean, it's a little bit of an improvement if you want it, but as we saw in if you look at some of my previous videos on regressions, adding more variables can cause noise. It can cause coefficients that are kind of misleading. So it might be better just to go with the one variable case if it's giving pretty much the same accuracy as these with more variables. So the main takeaway from this, and something very surprising, is that on the Titanic, sex was the main predictor of your survival, as we see from these high numbers, which don't get much higher later on. So the next thing we want to talk about is kind of take a little bit of a diversion into why the linear model is predicting so much better than, or not so much better, but predicting as well or marginally better than the logistic model, when the logistic model is the one that's made for classification, putting things into bins, either 1 or 0, things like that. So let's go ahead and look at the graph and just kind of take a few takeaways from that. And then we'll go into our last kind of regression, which is lasso regression. Here we see the actual scatter plot of fair versus survival status in our data set. The sizes of the circles represent how many people live at each node. So for example, if there were multiple people who paid $50 and did not survive, then the circle at the coordinates 50, 0 would be bigger, depending on how many people there were. This is kind of because if we don't make that circle bigger, then it's going to keep overlaying point after point on there, and we won't know how many people are actually at that point. So basically, you can just think of the bigger regions as a lot of people have that status, and the smaller circles as not as many people have that status. So we kind of see our theory confirmed in that we see a large clustering down at people who paid very little and did not survive. And we kind of see that the top line, which is representing the survivors, is kind of shifted to the right, which is what we would suspect. But it's not as dramatic, perhaps, as we would suspect initially. Now, the other stuff going on here is the red line represents 0.5, which is just the baseline for our regressions, as we were talking about before. The blue line is the linear regression, and the green line is the logistic regression. It doesn't look like a total S-curve because we're just limiting it, starting at 0, because there's no point putting in fairs that are less than 0 because they don't exist. So we see right away that the green line is doing a good job at predicting later on at higher fairs, but perhaps the blue line is doing well at predicting lower fairs. Let's focus on the logistic model for a second and see how many of these people it's predicting correctly. So how do we know how many people it's predicting correctly? Well, we go ahead and see where 0.5, that red line, intersects our logistic green curve. And at that point, that's kind of the transition point. So for all fairs below that point, it's predicting not survival. So all the actual people who have their coordinates below that fair are predicted correctly if they did not survive. And all the people who are having fairs above that intersection point, if they did survive, are being predicted correctly. So we see that within these green squares, these green rectangles, we have the correct predictions from the logistic model. We can do the exact same thing for the linear model, so it's just that our intersection point is a little bit different. It's a little bit to the right. It's the intersection of the blue line with the red flat line at 1/2. So we can see the exact same thing here. We see what happens is that the predicted not survived gets a little bit bigger, so we predict the people who did not survive a little bit better. But kind of that trade-off is that the predicted survived is predicted a little bit worse. So we kind of drop some people who we before predicted did survive, and we incorrectly classified them. But the real question, so let's overlay these two diagrams together to kind of get a sense of what is the trade-off here. So we have overlaid them. We see in this blue box, we have all the blue boxes, we have the linear correct, and in the green boxes, we have the logistic correct. So notice that the linear model gives up those two little circles in the survived category, and it gains that big circle in the not survived category. So it's kind of hard to tell whether that trade-off is a positive or negative trade-off, but if it is indeed a positive trade-off, then that kind of explains why our linear model is doing a little bit better job of predicting than our logistic model. So hopefully graphically this kind of A helps to see why the linear model is doing a little bit better, and B kind of helps to show everything that's going on with these regressions and how we're actually doing the classification and how the data actually responds to it. So now let's look at our last kind of regression. If you want to go ahead and watch the video on Lasso Regression that I made, go ahead and click here and kind of get a refresher on what Lasso Regression is. But I'll kind of explain it a little bit again, just kind of a crash course. So Lasso Regression is a type of regression not really used to predict regression coefficients because you're throwing in a lot of variables into here. So remember, when you throw in a lot of variables, the regression coefficients can become kind of skewed. So we're not doing this to predict accurately the regression coefficients. What we're doing this for is that Lasso is a kind of regression that will set many of the regression coefficients to 0 if it deems that these regression coefficients have no real impact on the thing we're trying to predict, which is survival. So in this model, we're trying to predict survival. So survival hat predicted survival based on these 6 variables. So this is basically all the variables in our data set that have numerical values. So fair, sex, P-class, age. So these 3 we're familiar with. Fair, sex, P-class, we kind of looked at those before. But now we're just throwing in everything else too. We're throwing in age, sibling, spouse, part. We could have also thrown in which port you embarked on, but that's a little bit more tricky because we might have to look at that a little bit later in a later video. And we'll explain why. But anyway, we have these 6 variables. And we're using Lasso Regression to kind of see which coefficients, which betas it's going to set equal to 0, which means that it deems that these have no real impact on the survival. So after doing this, we find that it sets to 0 beta 3, beta 5, and beta 6. So that means it doesn't think that passenger class, sibling spouse, number of sibling spouse, or number of parents' children have any real impact on your survival rate. And maybe we can attest to that because it seemed like passenger class didn't really have much of a sway in relation to sex when we were doing our logistic and adapted linear models. Now, what does it say for the other variables? It gives beta 4 a value of negative 0.002. It gives beta 1 a value of 0.002. So these have the same magnitude, just opposite signs. And surprisingly, it gives beta 2 a value of 0.06. So some takeaways here is that 0.002 and negative 0.002 have the same magnitude, but just opposite sign. But the main takeaway is that these pale in comparison to this 0.06. 0.06 is 30 times bigger than either of them. So as we saw before, this is telling us that sex is the highest indicator, the one that's most crucial, the most impactful in predicting our survival rate. So this 0.06 is very, very big compared to the coefficient of fair and age. But I guess some smaller takeaways is that age coefficient is negative, which is saying that basically the older you are, the less probability of survival there is, which we kind of said. And the fair is positive, which means the more you pay, the more survival you have. So now you're asking a question, right? You're saying, well, if these 3 are the ones with coefficients which are non-zero, then we should just ignore these, right? We should ignore sibling spouse, we should ignore parents, children, we should ignore passenger class. So why did we do our initial regression with fair, sex, and passenger class instead of fair, sex, and age? Well, the reason is this, and I did go ahead and run the same regressions with fair, sex, and age, but our accuracies were less, which seems kind of contradictory, right? Well, the reason it's not contradictory is that remember our original data set and how we had some gaps? Namely, there was gaps in the age column. There were certain people's ages which they, I guess, didn't record or lost or we just didn't know. So if we choose to do our regressions, our adapted linear and logistic regressions with fair, sex, and age, we need to remove all of those people who don't have an age, which reduces the size of our data set, which kind of causes our accuracies to go down, which is something that can happen when you have a smaller data set, smaller training samples, smaller testing samples. If we, on the other hand, choose fair, sex, and passenger class, then we don't have to do any removing of people because everyone has a fair, everyone has a sex, and everyone has a passenger class. That's kind of the takeaway here. So, which is why you have to make a trade-off. You can't just trust the lasso coefficients as they are. You have to see if there's caveats. In this case, there was a caveat in that not everyone had an age, so we didn't really include age, which is why I did the initial regressions with fair, sex, and P-class. So we did all this work. The main takeaway, I have to say, and the thing that's still surprising me until now, is that sex was the biggest, by far biggest, predictor of survival on the Titanic. The other takeaways are that adapted linear model can sometimes be superior to a logistic model, specifically in the case we did right here, we saw with the graphs. And the last takeaway would be that everything we did beat this 52.7% rate. So all those models would be superior to just shooting in the dark, using just this base probability to predict whether someone survived or not. So there is something to the Titanic. The columns do have something to do with survival. The next thing we're going to do, we're going to go ahead and build basically kind of a function that tells you how similar two passengers are. So assign a number between 0 and 1 to every pair of passengers that tells you how similar they are. And we're going to use that to do our own kind of classification. So we're going to have to be a little more creative after this, and it's going to be a little more interesting. So until next time.